All right, then we can start now. Yeah, hello everyone. I'm Claudio. I gave a talk yesterday about a similar topic as today, sort of like the first half of this topic. I remember some of you, if I'm not incorrect, but just like who wasn't in the talk yesterday? Okay, good. New faces, that's good. So I'll just like, at this point, I'll just like do a small recap of what happened yesterday. Very short, just to have some context. But in any case, I'm Claudio. I work for a consultancy called Erlang Solutions. We have an office in Stockholm and other ones. I'm based in London. We normally work with primarily with Beam-based technologies, so Elixir, Erlang, other products built on top of it, RabbitMQ, things like that. Which is, I guess that's why that's the primary reason why I mostly find myself talking about Elixir-related topics. So what we're going to talk about today is a library called Flow, written by the Elixir core team. Now, saying we talk about the library, that's correct, but if you don't use the language on a daily basis, or if it's just something that you don't necessarily have the opportunity to use from tomorrow or maybe from Monday, there are certain ideas that you can try to somewhat to carry over in your language of choice and try to maybe find some implementations or some libraries or some patterns that you could reuse, just because some of them are just generally good ideas. So there's no point in limiting to a language. So let's talk about collections of things. So stamps or no. Let's talk about collections in programming. So collections in a broad sense, and this is why the reason why we start with this is because the focus of the Flow library we're talking about is processing of collections. But we can keep it in a very loose term, which is either finite or infinite, doesn't really matter. The language has a construct which is a stream, which we're going to dig a little bit deeper into later on to represent infinite collections. But anything. Any kind of finite collection of especially of a big size, if you can talk about like even a few million items, that's fair enough. That's useful as a sort of like order of magnitude for what we're going to talk about. We are particularly interested in on collections where processing can be parallelized. So whatever you need to do with them, basically you have the idea that you have to perform a calculation, whether it's just a single value out of it at the end, or a sliding window calculation, so emitting values over time. Anything you can think of, where parallelization becomes pretty much the only way you can make it faster. Like if you do this calculation completely sequentially, you can start from the assumption that it's going to be extremely long, so you need to find a way to parallelize it. Even when parallelization is not obvious, even when you still have to somewhat reduce over a state that you carry across, parallelization may become, even with state, more desirable with just very simple benchmarks. Finally, there's an idea in the language which is common to other functional languages, which is the idea that collections of any kind are enumerable. And it's worth mentioning this because enumerable is basically, in general, the interface that we're going to use for when we want to start processing things. So in both methods and both approaches that we're going to see for the rest of the talk, the main difference is that everything is sort of like locked down in a potential state until we start enumerating it and until we start applying enumerable functions on it. And that's important to keep in mind because the fact that enumerable enumerable things, when you start to using those functions on them, that's when it become concrete. That's when you get really eager about their processing. So the more you can avoid doing that until you need it, the better it is. So streams. Streams as an idea, as an infinite collection of data, are implemented in the language with very specific properties. So they're essentially lazy enumerables. Like their API through the stream module, it's sort of like a one-to-one overlap where appropriate compared to the enumerable API. With the main difference that if you take a collection and you enumerate it, so you map over it with enumerable, you're basically doing that the moment you write that line of code. The moment your runtime gets to the line of code, it starts executing that. On a stream, you basically put in a data structure, which is the stream data structure, which is a data structure that doesn't have a particular shape. It really is just a struct in the language. But you basically put that, when you start to map over it, and you just basically queue an operation on it that will eventually be executed when needed. That means that in itself, streams may be extremely efficient for memory usage, because the main property that they have is that they only encode instructions on how to get more data, but not the data itself. And they also carry across sort of like a pivot point, a cursor on where you got to, so that you can basically move across this cursor and then take things only as you need, and then load more only when you need to. And they can be passed around efficiently because they are just plain data structures. So this makes it very easy to, with some very basic limitations, but you can pass around the stream across an entire cluster of machines, and then there's just data that goes across, and the overhead is pretty minimal. So with this idea in mind, and without going to an overview of the library first, because I think that's a bit more confusing than needed. It's much better if we start directly with an example. So the example we have, we're gonna use something that is it doesn't have that much data, but it's just very expensive to fetch. And the idea is that we want to fetch all of the repos that in this case, that I favorite across my life on GitHub. You can obviously use your username if you want to. It's not particularly interested in itself in terms of content, but it allows us exercising the stream API and flow with specific performance constraints. Because accessing basically all, I'm just going to say favorite repos instead of starred repos, because it's a surprisingly tricky word to pronounce for me. I don't know why. So it's a paginated HTTP API. There are other ways to access GitHub data, but we're just going to stick with this. And so it's at the current point in time, the entire history of the repos I favorited spans across 15 pages. And so if we want to go through it in its entirety, we make basically 15 paginated HTTP requests. Fetching that, what we're going to do, we're going to fetch some of those, and we're going to process and do some aggregation on them. The basic aggregation we're going to look at towards the end of this talk will be which ones were favorite and which point in time. So this kind of like group things together over a specific window of time. That's one of the most common use cases with the library. That's also one of the things that you may want to do about that in general. Basically, you start from maybe like a lot of data, and you want to slice it through and do some aggregate calculations. That's pretty much what the library was made for. In terms of data, it would be a list of these things. So this favorite repos, where there's a little bit of metadata. We're gonna basically work primarily with this dimension, which is just when basically if you if you remember the GitHub UI, you're basically gonna say, you can say like start this repository. The point in time where you press that button, that's when this timestamp gets created. At the end of the talk, there's a link. I'm gonna you can the code for this is open source. The examples are fairly contrived, but there's enough code in the repository that if you want to experiment yourself and do different kinds of calculations based on other params, just for fun, you can do it. The only thing I would say is that, which I got caught in this, is unless you have an authentication token with the API, you're going to be rate limited, which is not fun when you try to debug why it's not working, because everything comes back as empty. So just so you know, if you have a token, it's better if you add the token straight away or lose half an hour. Let's talk. So we know somewhat like what we want to do in terms of like going through this API. How do we sort of like put that down as the first building block for the calculations we want to make? So if I mean, I know the talk is about Flow as a library, but realistically, this function, if you really have to remember just one thing of this talk, that's one of the most important things there. Once you know about it, you're going to find all sorts of other ways to use it. So stream resource as a function allows creating a stream out of 3 basic components, which are a start function, an X function, and a halt function. It's worth spending a little bit of time looking at this because it gives us an understanding of how internally streams work and how they basically are implemented. When you see them used in the language and in libraries, how under the hood can be implemented. So in our case, it is very similar to the way you would consume that API with an API client, meaning you start from a username and then you can just basically compute, and that's the start function. You compute the URL you want to go to fetch the first page of results. Now, fetching the first page or fetching any page is always responsibility of the next function. So any URL, and even the first one, can be used to go forward, and you fetch the entire page, you get the elements out of it, so the 25 repos at a time, which represents the data, and then you don't have to, but because the GitHub API exposes hypermedia links, so they tell you pretty much in a part of the response what to do next. So which page goes forward, which link goes forward, which link goes backwards. So you take that out of the response and return that as a value. So the return value of the next function is always data, and the term, the item, or basically the param that can be used to basically recurse on the same function next time the stream needs more data. When you run out of items, you halt the stream with just by returning halt and a reason. And that gets passed down to the halt function, which may do some cleanup. The use case here is that if you start the stream over a file, for example, in the halt function you will close the file so that you do proper cleanup. But this makes it really powerful because there's one thing which is very important about this, and it allows us to think about this API from 2 different points of view. So internally in the stream, we're still thinking about pages, right? Because each time an X function goes on and ticks, we fetch an entire page. However, we don't use the page as an abstraction to expose that data because the stream, because the fact that we return elements, so we return in the data, we return a list of those repositories, means that consumption is separate. So the first time we pull, for example, 10 items out of the stream calls the API, fetches the data, we got 25s, we pull out 10, we got 15 left. If we pull another 10, the stream will not go and try to fetch more data because there's still pending data left. So the moment we fetch another 10, and we basically reach total of 30, that's when we would trigger the next function. So this way, we can keep separate consumption from fetching, which is very important. That's basically key for improving performance later on. Now, even with this, how would you do sequential processing? So like we built in Elixir standard library methods. What you could do is basically just say, start with a resource, and who has never seen Elixir before? Okay. So this operator, which is called the pipe operator, takes what's on its left or above and passes it as a first argument to the function on the right. So this, which is my username, is the first argument here. The return value of the first two lines gets passed as a first argument to the take function. So, and you go on and on and on. So it works exactly as a Unix pipe, and it just allows you to write things sequentially top to bottom instead of being wrapped inside to the outside as you would do in other languages where you have to wrap around to use the return value of an inner function for an outside function. So all in all, like this allows us to basically reason about things as a step on each line. So that's what we're going to do here. So we take the stream, and then the moment you call enum take on it, which takes 100 items out of it, the stream starts running, and it fetches 4 pages out of it, because it's 25 per page, so to get 100, it basically calls the next function 4 times. But it's a blocking call. So until basically it calls sequentially the API 4 times, it's not going to jump to this, it's not going to return here. And then after that, we map over the results and we take out the starting date. So what happens in this implementation, which is it's a straightforward way to do it, is that we pay an enormous tax up front here. So the properties of this implementation is that we do have a delayed side effect, meaning we don't touch the network until we start to ask 100 items out of it, which is also essentially the number that determines how many pages we browse through, because the next function is called the minimum amount of times to achieve that result. If we asked 101, it would be 5 times. The order, and this is another thing is important, the order of what we do with processing is actually important because everything is eager when you talk about enum. So this function, and this is like, I'm not sure how subtle it is. I found it subtle enough the first time I came across it. But because we reverse the order of map and take, the order here will exhaust the stream. So basically, we're going to fetch the entire 15 pages, then map, and then take 100 items out of it. The end result is exactly the same, except that this one is at least almost 4 times slower, because it's going to fetch 12 pages that we're not going to use at all. So it's important when you use enum with streams to make sure that you're doing things in the right order, even if the return value is identical. And yeah, it's not as straightforward as it seems. Like you may fall in this trap more often than people think. So how do we improve this in general, assuming that we have the correct order? Well, let's think about how we can make this processing in parallel to Flow. So Flow as a library is built on top of GenStage, which is the other library I talked about yesterday. So if you want to see the underlying pinnings of this library, I would recommend waiting for the videos, or if you can travel back in time, feel free to do that. I will not remember anyway, because I just have a different memory of you in the audience. So let's stop with the time paradoxes. So it's built on top of GenStage, which is more like a set of lower level building blocks to build distributed computations. Now, it's demand-based consumption. So because it's built on top of GenStage, Flow has the same main property, which is data is pulled by consumers and not pushed by producers. So you basically get data in when you're ready to process it. The speed is regulated, and we will see how we can regulate it. But you essentially go as fast as you can without inflating memory, and that's the main property that makes it particularly suitable to work on large amounts of data, because you don't have to load the entire data set in memory. So you can go through it piece by piece with different behavior in terms of memory usage and garbage collection. And the stages, which in the case of, when we're going to say stages in this specific context, it is from a GenStage point of view, each stage is one of the pieces, a producer, a consumer, one of the pieces that you use to lay down your pipeline. In the case of Flow, stage can be exemplified as basically a line in our code. Every time we call a function from Flow, from the module Flow, we are most of the times under the hood preparing a stage. Now, it's not a one-to-one mapping, but as a mental model, it's useful to keep in mind. So how does that work? Let's see this version of the code, which is slightly different. But we start from this, which is the same stream, and then we say, okay, prepare a flow from an enumerable. Now, anything that implements the enumerable protocol in Elixir is enumerable, which I realize is a bit of a self-describing thing. But in our case, it just means that whether it's a list or a map or a stream, they're all enumerable. So we lay down a pipeline from this specific enumerable object. Then we say, okay, what are you going to do in this pipeline? Well, we're going to map over each item and take out this date and return this date, sorry. And we're going to take 100 of them. Now, it's important. Here there's a slight distinction, but it's actually one of the most powerful things about the library and about like the ideas here. Like, flow.map does not execute anything. Flow.map just says, this is what you're gonna do. So it's gonna lay down a blueprint of future work. That work doesn't start until you start calling enum on it. So the rules are always the same. Enum kickstarts the actual work. Before, it's just instructions on what to do in terms of future work. That also means that while before the order was extremely important for performance reasons, when you lay down subsequent operations with Flow, the order becomes important for different reasons, but not necessarily for waste of data. So we're gonna focus on it like in 10 minutes basically. But at this point in time, you can think about this as a way to describe a computation without really executing it, because the return value of this flow map is essentially a data structure, similar to a stream data structure that says, this is what we're gonna do, but it doesn't do it until you start to call enum. Now, how does this get executed? Under the hood, the moment you start taking things out of it, instead of just doing everything in the calling process, so in a sequential fashion, Flow will put down an infrastructure of enough processes to do this work in parallel. The default settings tend to map nicely with the amount of cores you have on your machines. So there's a little bit of abstraction in between, but if you have a recent laptop with 4 cores, it will probably take over all of them, assuming that the amount of computation is enough for you to notice, because like it wouldn't happen you wouldn't see much with this example, but if you work with like bigger data, you would see that. So what are the properties of this? They're very similar. The side effect is delay until enum is used. So the behavior difference is in that respect is 0, which makes it a nice transition. The next function is equally called as many times as needed, because in the end, the amount of items we're going to pull out is the same. The order is less important for all intents and purposes from what we've seen so far. As long as enum is at the end, we know that nothing happens before that. The processing will be parallelized. Now, What are the, so, and that's one first level of optimization that this guarantees is that given I have this amount of data, I want to divide and conquer it so that I can do processing in parallel over subsets of that data, so that by the end of it, I just save time because I don't have to wait. That's one possible level of optimization that covers purely just taking advantage of the cores you have. But that's just for parallelization. From the concurrency point of view, what you can do as well is, because you know you're going to fetch data more than each sort of like page of the stream, then nothing should stop you from fetching enough data, start processing it, and in parallel and concurrently fetch more data, so that you basically have a much better pipeline where no elements are left idle. Until, like, the point is that you want to have idleness only when you got nothing left to do at the source, not when the source has still elements in it that you care about, but you're just waiting for things to happen internally. So you want to optimize for idle times. So we want to start processing while fetching. The two things should happen in parallel. And Flow gives us to do that, but it gives us a way to do that. But that's one of the basically two gotchas that people fall into when they start using it. By default, the default values that are used to control these properties, they work with collections of hundreds of items, which when you start working with this, and maybe you think like, I'm just going to try it out, and I'm going to try it out with a small amount of data, then it's going to be awkward because you don't see the effects you expect. And that is purely because the defaults of the library work with a slightly different order of magnitude than, for example, your test case. In our case, that means that we're going to have to make this change to the code. And we're going to talk about like regulating demand. But this just by allowing this change, if you test the code base with and without this, you're going to see pretty much a day and night difference, where without this param, it would basically have a behavior that would be pretty much sequential. But with this param included, it becomes, it starts optimizing idle times. Now, what is that? What's that max demand? So the idea is that we need to regulate demand with a minimum value and a maximum value. And that is conceptually, the names of these two params are like, sometimes they're a bit misleading, but each stage basically says, let's say that I know that I can process, it makes sense for me to process at least 5 items at a time. But I know that I can handle more than 15, right? Those are my limits, because that's how much I can juggle. So by expressing that with a min demand and a max demand, what I tell the stage before me is that you have to give me at least 5 elements, otherwise I'm not going to do anything. But give me enough so that I have at least 15 at a time that I can work with, no more than that. So with that specific constraint, it means that what happens under here is that we decide we want 100, and we set a demand, this max demand is 10, so we're going to tick in the stream, fetch the first page, that returns 25 results. That means that we can start processing, because we said that the maximum we can handle is 10. So the data will flow through the subsequent stage, and we'll start mapping. And I'm filling the final enumerable here, so we're going to start with 10 mapped, and we get basically a list with 10 items. We're not going to see that because we haven't got to 100. But when we pass those 10 items downstream to this function, then this level is already asking for another, sorry, we pass down 5 because it divides by 2. So it's asking another 5. So it basically pulls 5, 5, 5, 5, 5 at a time, because by default it just does this number divided by 2. And so we basically pick 5 elements at a time in a continuous fashion. And as soon as we got to the point where the stream is exhausted, it fetches the other page. Now, because our processing is very short, it's you see this thing in batches. So you see like 25 items processed at a time, because you just basically exhaust the entire page very quickly. But there is a perception thing, because you actually do it. Yeah, it actually does it by one chunk of 5 at a time, because it regulates demand between 10 and its half, which is 5 by default. You can control them independently, but you can basically regulate this by yourself. Now, that's the main thing. So for slow streams, which is our stream, you need to keep them a low value so that we can move at a certain speed. This is all benchmarking. Like you basically have to try out different versions and see which one performs best, depending on the computation you do afterwards. Now, aggregation. So aggregation. So what we want, there's the kind of the use case that we talked about before. We want to basically take this data and sort of like put it in buckets where we can see what was favorite in what month. So this initial version of that calculation that we could do, where we say start in the same way, and then start to group by month year. That is just a function that basically takes that date and basically puts it in a string that is year dash month, just because we don't want to group, well, December of 5 years in a single bucket. So it's very much it just basically gives you back a string key that represents a month in a specific year. So we want to group by that specific property. And then we want to take out 5 elements out of this in a sorted fashion, where basically we sort based on that month, so that we always get most recent ones first. So we start from the most recent ones. And finally, we make this a list. Now, we already defined how much we need in this call, so we don't have to say take at the end, even within them. We can just say like, okay, give me a list. That list will be limited to 5 elements, because we described that in a previous line. So this is like kind of like, if you could write this with just enumerable methods, and it would be very similar. But this way we start to do something slightly more sophisticated, which is grouping grouping over a specific key. Now, the API is not complex, but it hides quite a good amount of machinery underneath. So we kind of have to dig deep into it, because this specific version of the code, depending on how your data looks, will be buggy. So the idea is that we stream all the items, we group them by month year or year month, depending on what you like, and we sort them. But the end result is that the list has duplicate keys. Now, and that's actually a problem that once you try to look at it from a very physical point of view, it becomes much more straightforward to understand. So if you imagine that you have all of these items that basically overlap at the course of 2 years, and each month you've done something. So you've got like a nice distribution. Now, if you say, and that's what the library does under the hood actually, I'm the stream, I've got all the months, and I pick 4 people from the audience. Each one of them, actually 8 people, each one of them represents a quarter over these 2 years. Actually, sorry, they don't represent a quarter. I just pick them randomly, and I start like giving out things to sort and group. So 2 people may receive events belonging to the same month, but each one of them works with a separate bucket. So by the end of it, you're going to have 2 people that have maybe like 3 elements for June 2016 each, and the library doesn't know how you want to merge those 2 things. By the end of it, it has like a basically 8 or 4 or 8 key value lists with duplicate keys in it. But at that point, you would need to merge them manually. That's basically a side effect of parallelization without a strategy, just by randomizing work over different workers. And that's what happens transparently, under the hood, here. When group by does it, group by basically lays down by default 4 other processes and starts giving things randomly to them. They're going to do the things they're supposed to do, but by the end of it, the result will be will show duplicates. So how do we fix this? We need to introduce the idea of partitioning and or consistent partitioning more explicitly. If you used any kind of like distributed data store in the past, this may sound familiar in the sense that we're gonna have to think about hashing this data in a certain way. So we saw the problem. You have two repos passed to two different processes, and data may become duplicated. Partition means that we want to apply a specific rule on how these elements are distributed that makes the operation of merging the data at the end much more straightforward. Now, if you think about those people before, if I said, I'm going to give you only results to group, but they will all be from the first quarter of 2016. And then the second person will have second quarter, and so on. By making that decision up front, the operation of merging that data together at the end will be much more straightforward, because effectively all of these quarters will be completely disjoint. You just have to put them together. But there won't be duplicate groups, because June 2016 will only be one specific person. So that's what's going to happen. The merging operation at the end, with the improvement we do, is going to be much more straightforward for the system to do. And in fact, the data structure we're going to get at the end, which is a list which could have potentially duplicate keys, will not have them anymore. So that's how we can do that. Before grouping, we partition, and we say partition on the start on this key of the repository, and to hash, to basically create a routing rule, you hash to that repo with the month year. So the month year is the function that hashes it, which means that each worker will basically receive only one month. And by doing this, we basically create as many workers. Well, not really, but we're basically you can think about it as each bucket overlapping with one of the keys. The runtime may decide to optimize this differently, but it will be consistent, so that you will everything will fall into a predictable place. And because we use the same logic here, the same key here, and the same key in grouping, that's when things fall into place very easily, because we route things in a way that we also use to group by afterwards. So that's important as a way to describe this computation, because it allows you to optimize without losing correctness. So that's the second biggest gotcha. Like, first one was like min demand and max demand. The second one is partitioning data. That's the kind of thing that it's subtle and it's nasty, because maybe your data doesn't have that problem when you do it the first time. Maybe you have like things that wouldn't show that problem, but the moment you do, you're going to start to scratch your head. The other thing is that the return value of all of this computation is a list of tuples, and the list of tuples may contain duplicates. But if you decide to put that inside a map, which doesn't have duplicate keys, the moment you do that with built-in tools, there will be data loss, because keys will be replaced. Values for identical keys will be replaced and not merged. So it's the kind of thing that you have to think about it. Otherwise, you will basically get into a scenario of data loss without even knowing, because the computation will look apparently correct. So streams are powerful, and flow can be used to model parallelized computations, but the gotchas are important. They are avoidable, but it requires a little bit of reading around partitioning. There are other things we couldn't fit in 40 minutes, which are interesting about the library, which is also like you can do calculations over windows of time or amount of elements, and basically get batches out. Like, for example, like give me all of this computation every 10 seconds and things like that. So I would encourage you to read the documentation for that to see how you can do with it. But that's pretty much the gist of it. Okay, thank you. Now, 3 things to like basic page of the documentation. The example application, there's instructions in the README, but basically there's a slightly extended version of those examples that you can run, pretty much like do a mix run with the name of the file, and that's it. And again, there's a, I linked it to this yesterday again, for the mindset around all of these libraries, José Valim's keynote, the LexicCon 2016 is a good rule of thumb. If you need anything or any question or anything like that, you can reach me at any of these addresses. So feel free to do that if you need to. Thank you.